continuing when there's a lot of data and not a lot of time. Not only results, but the way you train neural networks is important, from classical backprop with its deepness and the limitations in the industry to stochastic configurations. What works in a more stable way on the real production line? And we will learn that just now. Professor of the University of Science and Technology of Qingdao, Dianhui Wang. Questions, problems, and developments in the field of machine learning.
Hello. Very glad to have opportunity to talk something in Russian. So that's my first time in this country. I think I spent some time travel around in the last 2 days. I found Moscow is a quite expensive place. Okay. I think today I will share my knowledge and my research experience on machine learning. Okay, so what I will say are issue, challenges, and development. All right, so this is especially for application for industry. Okay, people talk a lot about machine learning, deep learning in the past. But from my perspective, for real industrial application, okay, or we talk about industrial AI, I think not enough. People start being aware something, okay, but where is the solution? So that's really, I think, significant for further development. Now, I think, let's see, where I'm living. Indeed, I'm Australian citizen, okay? My home is in Melbourne, Australia. But now, for some reason, I came back. Now, I'm living here, okay? So here is Beijing, and here is Qingdao, right? Here is Moscow. So this is a city where I'm living in now, Qingdao, okay? So it's a coastal city, okay? Very good environment. That's a university I'm working. Now, I think some philosophy for doing research. I think different people have different opinion, okay? To me, I think we need to understand something. Everything we hear is opinion. Probably not the facts. Everything we see is perspective, not the truth. Okay, so this is from Marcus, Roma Emperor. Today I will talk, I think, 3 things: challenging, development, and perspective. That's from my personal point of view, okay? I think in the end, for doing research, I believe logic will work, and the great tools are always simple, okay? That means if you make the learning algorithms very complex, I don't think it's a good solution, okay? Now, I think let's talk something about AI technology meets process industry, okay? Composition of process industry, we have a device, we have a material, and then we have parameter, okay? So this process parameter really matter. So will affect maybe the power, the energy you used. Also will affect the quality, stability of your products. Okay, that's obvious. Then we have some association with machine learning about this, how we can make these products stable and how to save energy. So here we have several things including modeling, automation, and intelligent control. So that's indeed my background from computation math and went to control theory. At the end, my PhD is industry automation. So that's why, so I can understand this stuff, okay? Now, take a look. Lightweight model we need in next generation of industry automation, okay? So it goes scalability, so that means we use edge computing-based, IoT-based application, okay? So we have a system adaptation, so we need a very fast tuning of your machine learning models, okay? And then real-time optimization, so far we have a neural net solution, different heuristic solutions. But to my opinion, I think probably we should go to randomized approach. Okay, so randomized approach, we never seek optimal solution, but feasible solution. Okay, and control algorithms. So nowadays, I think very popular. People use PID, and sometimes for delay system, PID doesn't work. So most of industry partners, they told me they are interested in developing nonlinear or adaptive MPC, so model predictive control. So in model predictive control, what's a big deal? A big deal comes from the model, predictive model. So that's to say, modeling, you build predictive model so the model can work with a high accuracy and robustness, okay, against some external environments change. So this is very important for industry, okay? So all things, I think, are certain, okay? Probably from the sensor, probably from the careless of the operators, nobody knows, suddenly changed, uncertain, okay? So in such environments, how we use the collected data to build a model, so the model can perform as expected. Now, so the first part, let's talk a little thing about issues and challenges in machine learning. The first paper, very influential, I think published in Nature, okay, 1986. So 1986, this paper is talking something about this type of neural nets. And ideally, the neural nets feed forward, fully connected, we call it a multi-perceptron model, right? But this model cannot be trained because the active function is step function. So that's people feel very difficult. How to we understand the model is capable to solve some problem, but the key is we don't know how to find the parameter of the model. Okay, so that time, I think the paper come out, published in Nature, and people talking about we can use this sigma model function to do approximation of the step function. So in this way, we can use the backpropagation, gradient descent approach, very simple mathematical optimization solution, right? So that's old time. After this work published, I got thousand work published in different way to improve the learning algorithm, even use fuzzy logic. Okay, how to change the learning rates, how to initialize the weights, a lot of work. And then the next year, 1987, so 3 groups of people from Japan, from United States, from Germany, they published a piece of work, okay, talking about universal approximation property of such a network model. Now, I think 2 years ago, a group of people from Cambridge, Oxford, UK, they have a workshop talking about these kind of things. Neural nets, robust, reliable, how to improve these performances. Then I gave a talk. I think in the end, people, after discussing, we conclude something. So universal approximation property just gave people hope, but nothing to do with design, okay? Because here, I believe, probably you know neural nets. You train neural nets and put this model into practice, okay? But the first thing appear on top of your mind is how to design, okay? How many neurons in the head layer? How many layers? Nobody can give a very clear guideline. Okay, so this is the current status. Now, because of this, so people already, when I can't say exactly wrong direction, I have to obey the facts. So backpropagation learning algorithm promote these AI developments. But I can't say too much about this. Okay. Maybe wrong direction, okay? Now, you say, why backpropagation? I will show you a simple example, numerical example, then you understand why we have to think the backpropagation is something, okay? Now, let's have a look at this simple numerical approximation, a function approximation, okay? So the blue is the function to be approximated. Now we run MATLAB standard tools, okay? I show you different epochs, so 50 epochs, and the neural net model perform like this, the red line, okay? So I don't think you will be happy with the performance, right? After, I think, 2,000 epochs training, we spent 35 seconds. Do you think you are happy with the performance? I don't think. Lots of people talk too much about learning, deep learning, but nobody really pay attention. So this is totally wrong. We have no trust, no confidence you can get a model well trained to perform your task, okay? So this is a very simple numerical example. You can imagine if the task became so complicated, how you can believe your model, your training algorithm works, okay? Now, another practical case study. So the data is, I think, from Northeastern University. We try to predict these three parameters. So this material. These three parameters play key roles. So let's try to use backpropagation, MLP with backpropagation, okay? So you look, we made 100 trials. The green is the area for generalization, prediction, okay? That's, I think you can see, very unstable, okay? What's wrong with this backpropagation? Because initialization make a difference. So every initialization of the weights can result a new model, and the model converging to local minima. Okay, whatever, done, finish. So then I test the model, okay? So you get 100 trials, and then the error very unstable, demonstrate this instability. So when people talking about reliability, do you think the reliability of this MLP with backpropagation is good? I don't think so. Very unstable. So I have developed with my students some we call the stochastic configuration network, and then the performance comparing with this backpropagation based MLP, I think much improved. Okay, so you can tell that's a prediction performance. Okay, now let's say something development of these machine learning techniques. I'm citing my stuff. Okay, that's a stochastic configuration network. Now, that's I think I feel is original, innovative, and then real-time data processing, and then we tried to interpret the precise how we construct this model incrementally. Okay, now I just show you the example, the same example for function approximation. I use just 33 epochs. I spent the time 0.36. I can build a model exactly like this. 100 times faster. But I can make very accurate approximation, as you can see. Right? So this simple example shows something, demonstrates so this stochastic configuration network really can work. Okay, especially is a lightweight model. Okay, that's why today I came here. I spent 9 hours and 40 minutes from China flying here. I share with the knowledge with you. Okay, now I just let me introduce briefly what I say it is. We have different versions. You can find it, even you can download the code from my research homepage. So this is, we have a term called a bridge MLP. Multi-layer perceptron model, but we have a bridge MLP. So that means from input layer to the output, we have a direct link. Also, each layer, we have a link to the output. So this is a bridge. The lines in red, we need to evaluate. Other parameters, for example, in the black, random assignment, finish. One pass. And also, we have this incrementally constructed. Rather than given architecture, you tune the parameter. Doesn't work. Okay, even you think mathematically it doesn't work. At least, so the error for the learning, it cannot be zero, cannot be free, zero free. But this way, I can result the model, very quickly build a model, and then mathematically we proved. So that's error-free. That means universal approximation property holds. Okay. Now, this is a key contribution from my group. So that's published in 2017 in transsegment cybernetics. So here is the key contribution. Before, all randomized learning, so they have no constraint, illogical thinking. Simply, they assign random parameter here in the black lines, okay? And they evaluate the right line just using least square. So very fast. You can see thousand publications about this. I do believe somehow is misleading or poor understanding. Okay, so I'm the person just brought this illogical understanding, and I think draw a right direction for this randomized learning. Okay, let's have a look. Sorry, because this is diamond, I don't know how to control this. Doesn't matter, okay. So let's share some practical application, so real case study, okay. So you can have a little bit more belief about this action, okay. So this we have a data-driven software sensing system. So that's widely used for industry. Okay, that's inputs, and then we try to predict this grading particle size. Okay, so currently still I'm in the loop, still in precise this project with a big company. Okay. So now what I'm trying to show you is the comparison results with the well-known MMP, okay, trained by backpropagation. Look, MLP, this is a training performance, a test performance, and ours, so RVFL is a constraint-free randomized learning algorithm. So random vector functional link. Still, a lot of people around the world, they still trying to use this RVFL, but theoretically, I can prove, okay, cannot. ISN always outperforms than RVFL. So this is the work we published in Transaction Industry Informatics last year, okay? So obvious, so our ISN can outperform. Now, it's another example. So currently I got involved. I'm the director for these, the key contributor for developing intelligent control system. Okay, so this system is very difficult to be controlled. Very valuable, but very challenging. Okay, so this is polysilicon reduction furnace. Probably you don't know. You can check after this meeting, okay, conference. Now, let's use the closed loop data to model, okay, because I have no open loop data available, only closed loop data available. Okay, let's use the closed loop data to build ISN and see what's happened, okay? So this is the inputs, and then we have the output. So in total, we have 42 inputs, but these inputs we are sampling, okay, some inputs in different time instant. And we have 15 output. So this voltage and atomization level. So this is very important because we can't measure the temperature on surface. So no other ways. We have to do some indirect way to control the system. So hopefully this design, this MLP will have a good performance. Okay. Indeed, PID stopped working for this system already. Now, let's have a look at the performance. Okay, so we set up, set up the experiments like this. So 24, and the first layer, 903, and the second layer, 304 neurons. Okay. Then we spent probably 2 hours time. We got the neural net stuff. If we run MLP, the same architecture using backpropagation, forget it. Maybe you get maybe 1 day time. Okay, converging very slowly, and then the performance is very poor. Okay, so let's have a look at what are the results we obtained by using stochastic configuration network. So indeed, it's a deep version. We applied these terminal conditions, stop, early stopping. Okay. Also, we applied regularization. We proved a small perturbation. Then now, 40 runs, the real runs from the industry, we collect the data, right? And then we use another 20 runs data to do testing. So you look, so this is the, I think just for 1 voltage. you can see that's closed loop data. So we can predict model perfect, right? You look at this atomization level using SAN, right? The truth backgrounds and the model output are almost fitting very well. So this is, I think, two industry case studies I show you, right? Now, I think the last part, I express my perspective on this machine learning, especially for industry application for next generation of automation. Okay. First, I think scalability and flexibility. Here, scalability, everyone understands. So we goes the machine to be controlled, maybe not a single one, a group, right? A group of tasks. So we have to consider how you design the control system in I think, IoT-based, okay, control system design, rather than like before, single one. And also flexibility here refers to adaptation capability, because the data we collect just like closed loop data offline. But in the real time, when we do this modeling, we have to tune the model using the nearly collected data, right? So this step, that's what we call the adaptation. So we need the very fast tuning. You think, imagine, if we have neural nets with millions parameters, can we do the job in real time? Because the sampling is very limited. For example, 3 minutes, even seconds, you have to get the job done, okay? Tuning the parameter, adaptation, the model. Now, I think AI and machine learning offer more intelligent solution. So these, I think, we can't avoid in the future, next generation of industry automation system design. So now, I think we have this AI algorithm on our hands to further develop. Okay. A lot of people think maybe generative model, large scale language model is really something, but this is for social, not for industry. You think of this for industry. Do you think that's a big deal? More important than social information technology, your retrieval with interactive. So this is, I think, people have to consider this. I heard a lot of competition among the nations in the future is how you can produce lightweight model. Okay, so stochastic configuration network itself is lightweight already. So I can use binarized weights in the model as well. Okay. Now, I think physics-informed neural nets already became, in the past 10 years, published a lot in Nature, Science, and relevant journals. So that idea is we have governing equations. So basically, it's try to solve the problem. Limited data subsets cannot generate a good learning model with good generalization. So this is the idea. So we have something constrained. We have some data available, collected. So how we use these two information to build a machine learning model. So here is something. I read a lot of publications, but I find still something wrong, okay? Not enough. Also, I believe, my personal opinion, I think knowledge-based informed neural nets should be a very promising direction in the future. For example, we understand output variable is monotonic with respect of special inputs. What to do? Can we embedding such knowledge into learning process? Okay, very important. Key conference reference, that's my master supervisor, my PhD student, my lifetime friend, Ivan Turkin from Caltech. Okay, I appreciate a lot. We discuss a lot and collaborate personally and professionally. Thank you all for your listening and attention. Okay. Yeah, thank you so much. My contact information, dh.wang@deephin.com, my research homepage, my WeChat if you are using WeChat. And here some advertisement opportunities for taking postdoc position under my supervision in China, if you like. Okay. No limits. The number is open now. We have CIC scholarship available. I think now it's still opening. If you like, you can apply online. So here, the last line is in Russian, so you can read easily. Thank you so much. Okay.
Thank you so much. Thank you for sharing your experience with us. Thank you.